setting up a more kind of robust testing framework. But I'm going to start digging into Vlad's sharding spec and stuff and work on CBC a little bit more. But just wanted to come in and be a part of the conversation. So that's all I have right now.
Sweet. Michael?
Yep, I don't have too much to report either. I haven't been doing any sort of original Casper research lately, just more of the getting proof of stake going in Rolang type stuff.
Sweet. Oh, well, tell us about it. I mean, do you have some contracts?
Nothing working yet.
Okay. All right.
But I've started. I've started looking at what, because it's all tied in with what the R-chain block, like how R-chain's state is internally represented on the blockchain is sort of important to what the transfer of funds and things looks like for the proof of stake. So I was chatting with Mike Stay and Kyle and others about that sort of thing. We have a running Google Doc right now, which is sort of serving as an informal spec for what these contracts should look like, and we'll hopefully write them up this week.
Sweet. Can you add me to the Google Doc?
I can definitely do that. Yep.
Appreciate it. Thanks.
Very exciting.
Yeah. Vlad, hey.
Hey, yeah, sorry. I just got my audio problems fixed. I don't know. I've been having problems with my Zoom microphone connection for a while. How's everyone doing?
Great.
Doing well.
Yep, pretty good. Pretty good.
Sweet. What did I miss?
Let's see. Danny gave a short and sweet update, and so did Michael. You want to go?
Yeah, but I'm also curious about what the updates were.
Okay.
I've been spending some time in FFG land, working on contract auditing and doing some kind of enhancing their testing infrastructure, but trying to dig into your sharding spec this week and see what I can do on CBC side.
Cool. You should see my sharding spec now.
Do you have an update?
Yeah, it looks a lot better than it did, say, like 2 days ago.
Oh, sweet.
I'm gonna try to share that with everyone, but I need a minute or two for technical difficulties. So if someone wants to give an update.
Okay. My update's a little bit longer, and I have to actually switch machines. I'm on my phone now, but I'm a screen share, so
that's exactly what I'm doing. I'm kind of setting.
Okay. Well, we can hang out. I just
we can race to the screen sharing. But
one thing I can say is the link that you gave me to the Casper Discord. I don't have write permissions on any of the channels.
Oh yeah. So I turned write permissions off by default for everyone. I have to make you a scientist.
Okay.
So it's like don't worry.
Poof! You're a scientist.
I don't know. You're not.
Yeah.
Hey, are mathematicians actually scientists?
100%. Yes.
Somehow, I'm not sure, but consensus scientist is kind of, I don't know. So computer scientists? Are computer scientists? That's really the question for me.
Yeah, computer scientists can definitely set up experiments, so they're scientists for sure. I think of it as like the experimental branch of mathematics.
Isn't looking for a counterexample kind of experimental design?
Sort of, not really.
Let's try to test our hypothesis.
Yeah, kinda. Yeah.
I guess there is such thing as mathematical observation. The question really is whether hypothesis testing is a significant part of mathematical reasoning.
Yeah, well, I mean, I definitely think it is a significant part of computer science reasoning. Like if you're doing, network design, so you have a hypothesis and you can, build out the network and then go test that or build out instances.
But is that computer science or systems, like distributed systems? I guess it's all
uh,
included in computer science.
yeah, I view that definitely as part of computer science. Yeah.
Okay, well, maybe scientist is the wrong label, but
Anyway, if you could flip the bit, then I
Mhm.
have a lot of updates to pump into the channel. So
Great. Yeah, happy to.
sweet.
Um,
Also, Christian, I sent him a link so he can, like, because last week we were all in the Moscow airport, and that's why we couldn't do the Casper stand-up.
yeah,
But we couldn't let you know because we didn't have write permissions into the Casper channel.
it was all right. No big deal.
But anyway, I sent Christian an invite, and if you could also flip the bit for Christian so he can give updates about the AV stuff, that would be a
All
good
right,
thing.
I'm going to talk to Christian. I'm thinking about maybe giving him a special role of moderator, if he'll.
Okay, great. Wow, that'd be really good.
Yeah, and then maybe we can think about allowing more roles. The reason why I have this is because I don't want to do any moderation, so I just kind of like have like a. It's easier than to do any moderation.
Yeah, I understand. Yeah.
So check it out. I don't know that I'm going to be able to do screen share, but what I'm going to do is I'm going to use my camera.
Yeah.
Flip it around here. Check it out. Tell me how you guys are doing here. Okay, so I've redefined things a bit since the last time I've given the spec, given the definitions in the spec, and I think it's a little better now.
bad.
This is awful.
Yeah.
It's strobing.
If you can just send us the link, we can try to follow along.
Okay,
Yeah.
sure. This is just me trying to hurry things up.
Yeah.
I can just try to get Zoom working on my Ubuntu, or I can.
Okay, well I can go first if you want. While
yeah,
you're doing
please
that,
do.
let me. I'm just switching over to the laptop. Hang on 1 second. It won't take too long.
I guess I can talk about kind of what I've done somewhat. Basically, I've kind of changed my definitions and given more definitions. I'm kind of like getting closer and closer to a kind of more complete specification with all the things being defined. And things are looking pretty nice. It's not. I don't have a huge update, but I just want to share like the different definitions that I have.
Cool. Anybody have any blockchain, Ethereum, Archain contacts in Japan while we're waiting?
I'm sure I know people who do, but why are you in Japan?
I'm gonna be in Japan for 3 months soon. I'll hit you up on Skype or something.
That's exciting.
Okie dokie.
Yeah, very exciting.
I can screen share now. People wanna.
Sweet. I think we're ready.
Okay, so I've spent the last week thinking a lot more, last week and a half, thinking a lot more about sharding for Archain. Sharding for Archain is done in terms of namespaces, and so there's been an internal discussion in Archain about how namespaces are related to Casper, and so effectively what I was doing was giving a sort of detailed spec on how namespaces are related to Casper, so that we can, at least as a straw man proposal, so we can take pot shots at it. So there was a lot of good dialogue about 2 weeks ago with Kyle and Mike and Michael and myself, where we were talking. There was a little bit of miscommunication, though, because there was a misunderstanding that I'm trying to clear up now. So I think different people have different ideas of what namespaces are, And so the first piece of the puzzle is to disambiguate the namespaces, which are kind of like, let me see here. I was drawing it last night and didn't get too far, but effectively, I don't know, you probably can't see this, but this is this is the set of all names, which is an infinite thing, right? If you start with the set of all URLs, right, that's clearly an infinite thing. And then, but then namespaces are subsets drawn from that set of all names. So it's a very, very big thing. But it's also an abstract thing in the sense that it's this complete lattice that it's the power set, or the power object over the set of all names, and so there are all kinds of operations that absolutely exist there, but we don't necessarily in practice ever explore that entire lattice, just like we don't ever explore in total any one of the infinite subsets of the set of all names. But all of the operations like sum and join and a bunch of things all exist on this lattice just because of the structure of the lattice. But that's different from the lattice of built from the power set of the different validators. So on the other side, we have another lattice, which is the power set of the different subsets of the set of all validators. And then what we're looking for is a relationship between certain subsets of validators and certain subsets of names. And what we're trying to do is to sort of build out a homomorphism that's between the lattice, the power set of the validators to the power set of the set of all names. And that homomorphism evolves over time. So it's not fixed, right? As the network evolves, or even let's just say as the network evolves, that homomorphism evolves. So even over the course of the execution of various contracts, when certain contracts complete, then certain namespaces may just never be served again. So you don't need any validators serving against that as well. So that's kind of the basic contextual background. And then what I was working out was how you work out that relationship. And so what I was sort of sketching out for the group goes back. I was just providing some background here. So there's an area of research that's closely related to the namespaces of our chain called region. Where you're able to reason about something that looks kind of like an abstract memory, and the effects on that memory. So you can actually do safe memory allocation and memory deallocation based upon the lifetime of regions. And it turns out that Andy Gordon, who invented, along with Luca Cardelli, the ambience, did some good work with Silvano Dalzilio on a variant of the pi calculus called the pi calculus with groups. And they were able to show that just with this idea of groups, which are really just groups of names. So this is kind of a precursor to the very rich row calculus idea of namespaces. So with just groups of names, they're able to give a full and faithful account of Mads Tofte's region analysis ideas. And so I just very, very quickly kind of show, I won't go into the region stuff because that's outside of the scope of this discussion, but I will just kind of give a quick indication of what a pi calculus with groups are. Hopefully people can see this. Is this large enough? I guess I can make it a little larger.
It's good. Yeah, it's good.
Yeah, it's
Okay,
fine.
cool. All right. So basically, it's just an ordinary polyadic pi calculus. So you have input guarded processes, you got output stuff, you got parallel composition, you've got the stop process and replication, and then there's the usual fresh name allocation right here, and is making a new group. It's and notice just syntactically, you can see that you can never send a group, right? You can only send names. So this is a completely static declarative kind of thing. There's nothing here other than declaring a group. And then it turns out when you look inside these T's can mention the groups. So what it ends up doing is one's pi calculus code can declare groups and then use the groups to restrict. And the important thing about this is that these groups are entirely abstract. They don't mention anything about network topology. They don't mention anything about validator sets or anything like that. They're literally just the names of some subsets, potentially infinite subsets of names. So you've given some abstract moniker for some subset of names, and we're using those abstract monikers to control the dissemination of names. That's all groups are doing, right? So you could think of them like permission groups or something like that. That would be one way to approach it. And that's important because then you can get a mapping from groups to validator sets, and that mapping can evolve over time. And then the other piece of the puzzle, the one that's kind of relevant for us, is that with an extremely simple type system, I mean, like, this is just barely more complicated than Milner's idea of sorting for the pi calculus. So here are your types. Basically, you have some set of name groups, which are denoted with the bold G and H. And then a type is really a name group as a label, and then a set of types, and then some hidden groups that represent your effects. And then you have a typing environment, which is the usual thing. Either the typing environment is empty, or it judges that a name of type T, or it includes the group G. And then you have several different kinds of type judgments. This is an Andy Gordonism. It's not common. It's not as common, let's say, in these kinds of typing specifications, but it's pretty well established within the community. So you want to talk about, when a typing environment is of good shape, when a type is of good shape relative to a typing environment, when a channel type declaration is legal with respect to a typing environment, and then finally when a process has a particular type, which is again one of these kinds of things. So it basically just says when a process supports a particular set of groups, and then the typing rules are extremely simple. Like the empty environment typed, assuming that X is not already given a type in the typing environment, and that E is a well-formed type, then you can give X the type T, and adjoin that to add that to the E and still get a good typing environment. These are the basic kinds of rules. The important ones, really have to do with input, output, and the new group declaration. So again, if we have that X has this particular type in E, and we have that these are the types for Y, and they're distinct from E, and that gives rise to P being typed G. Then if we do an input operation and prefix that to P, the type for P is just going to be the group G here, the one that was given for X, union with the type that you'd given to P, take away the effect that was associated with the type X, right? Very, very straightforward, nothing magical here. And then there's a corresponding one for output. And then what we want to look at is the new group. So if you have that, this group G is a part of this typing environment that includes E, and that typing environment thinks that P is of type H. Then we get that E thinks that the declaration of G over P is going to have type H take away G. That's it. There's not a lot to this typing typing judgment, and what it gives you is enough. Already, this is more than enough machinery to give a full and faithful encoding of the region analysis, where effectively groups represent regions, and I argue that this gives us more than enough to talk about a sharding solution, and in particular to deal with the kinds of issues that arise when we look at joins for the row calculus with joins, and then from that sort of a row calculus that has these kind of name group types, which are far short of the namespace logic, then we can give a static analysis which allows us to say when what are the name groups that a particular contract would need to be supported if it were to run, and then to check to see that there are validator sets that support those name groups. And then it becomes a matter of policy as to what to do in certain cases. So in particular, in the case where there is no validator set that is supporting one or more of the groups necessary to deploy the contract, you have to make a decision. Either you invent such a validator set and assign some validators into it, or you invent such a validator listing for various validators to join, or finally you defer the deployment of the contract until such time as a validator set is serving the groups that are necessary to run that contract. So that's kind of a quick sketch of the algorithm, and basically this is a soup to nuts specification. This tells us exactly of the contract out to the validator sets, and then it becomes a question of policy as to what to do about how to handle the case when you have a gap in the validator power, the power object for the set of all validators. What you do there. Hopefully that made sense. Any questions?
I can't. Do you guys hear me? Hello?
Yeah.
Yeah.
Okay, cool. I was thinking maybe what would help me is if you looked at my sharding spec that I've been working on just now, and try to help me relate the names that I'm using to, and basically it seems to me like, okay, I'm doing something much simpler than what you're doing. I'm sharding like, I just have like this kind of blockchain-like structure, and that I'll share with you in a second. Whereas like everything you're doing is like more tailored to a kind of consensus protocol that understands a lot more about the values of the consensus than mine does currently.
Yeah, that's exactly right. So the important point here is that we know that we're in contracts that are built on row calculus. So rather than taking a step backwards, the reason we're doing this is because namespaces are kind of automatically sharded. That's their purpose in life, and that's what the purpose was conceived of since 2002. So now
Yeah,
I'm
sure.
just now I'm just simply just sketching out what the rest of the algorithm is for that approach.
Okay, so here, let me show you the way that my sharding setup is set up right now, and we can see if we can find any kind of links or connections. Kind of.
Sure.
Let's see. So I'm going to share screen. Let's see if everyone can see this. You see my mouse also?
Yep.
Okay, great. So basically, I have some set of shard names, S, and I'm going to talk about the structure of that kind of maybe later. All I know for now is that I have at least 2 names in there. And D is the all possible block data. And then, so I basically am going to define the blocks on shard X, where X is some shard identifier, as this map from X to a block on shard X with some data, or as one of these merge blocks, which are basically B subscript X, like they define on the next line, where X is some set that includes X. So basically, B lowercase x here is a set of merge blocks identified by a set that includes the shard ID X. So if I block merges shards 1, 2, and 3, then that can be considered a block on shard 1, on shard 2, or on shard 3. And then there's like the genesis block for any given shard. And then the blocks that merge some shards basically have a structure of mapping all those shard IDs to blocks from those shards. And they also have block data. So the block structure basically looks kind of like I basically have like a blockchain replication for every shard with these special blocks that kind of merge the different shards together. You can also, I'm calling them merge blocks. You can also call them join blocks. And then I have this previous block resolver where, so like normally in a normal blockchain, you just like ask for the previous block and that's like well defined, except for, kind of at the genesis block. Here you
Okay, I see how to relate the two.
Here we need to say a little bit more. We say, okay, look, follow the previous block pointer down this shard, because we might run into a merge block which has a bunch of pre blocks, right? And then basically I have a little validity condition that says that, look, the pre-block pointer for any merge block B that includes some shard XI is actually a block in shard XI. These are kind of somewhat boring definitions, but you can define like, membership of a block in the blockchain of another one on shard X as basically whether or not it's accessible through the pre-block pointer on with like resolving on X. So basically, if they're the same block, it's the same. It's in the same chain, or if it's in the same chain as the pre-block resolver for that block given shard X. And then we can use that to define safety. But for now, let's talk a little bit about the fork choice rule. So I have the fork choice rule that maps like a set of blocks to a map from the shard IDs to blocks on the shards. And then we have a similar kind of faithfulness rule that says, oh, look, it maps X to a block on shard X. And here are the interesting definitions in some way. Fork choice enforced atomicity of merge blocks. Basically says, oh, for any merge block, if it's in the fork choice rule of shard XI, it's also in the fork choice rule of shard XJ. So this is kind of like atomicity enforced by the fork choice rule for just any merge block. So if a merge block is in the fork choice rule in one shard, then it like has to be in the fork choice rule of another. this is a little bit of a weaker definition down here, but for now, oh, here's the interesting one. Safety of a block on shard X basically means that for any future state, B is in the chain at shard X for the fork choice rule at shard X. And then finally, basically we have these two kind of weaker definitions. It's like enforced fork choice enforced atomicity of safe blocks. It basically says, oh look, if it's safe on one block, if a merge block is safe on one of the shards that it merges, then it has to be safe on the other one. And if it's not safe on, if it's not, and if it's not safe on the other. And similarly, if the block is safely excluded on one shard, then it should be safely excluded on the other. Definition 310 is, I think, the more interesting one because it's like the weakest. So an eventual consistency basically says, look, if block B is safe on a shard that it merges, then its exclusion is not safe on any of the other blocks that it merges. So it's not can't be safely excluded once it's been safely included, which also means that any blocks that compete with B are not safe. And here, basically, if you safely exclude a block B, then other shards that it merges didn't safely include it. So these are kind of the basic definitions that like kind of all the sharding specs that I'm going to look at are going to satisfy. And then what I'm going to do is kind of to make restrictions on further restrictions, so that this structure here has less possible merge blocks. And so specifically what I'm going to do basically is say for the binary sharding, I'm going to let the shard names be binary strings. And then I'm going to only allow merge blocks between binary strings that differ by at most one element at the end. So basically they're the same, except for one, the string is a little bit longer. To get this binary tree kind of structure. And I'm only allowing merge blocks between shards that have an edge between them. So like this shard can have a merge block between those two, between all these three shards here. Basically, I've kind of set up, in some way artificially my namespace, but the tree structure is what I mean. It ends up being useful for guaranteeing these properties. Well, I can guarantee fork choice and force atomicity of merge blocks, and that's what this first spec is going to do pretty easily here. Basically, with the later blocks, with shards, the children shards, the ones further down, having a fork choice rule that specifically is designed to maintain atomicity with the parent shard. So this fork choice was kind of free, and then later these ones will maintain atomicity. And so I'm going to have like the fork choice rule of the whole system guarantee the atomicity of these merge blocks. And so I can kind of say, why there would be some consistency when there's like cross shard state transitions, which would be, kind of in this data for the merge blocks. Anyways, Greg, so you mentioned that you saw the connection. I'd love to hear.
Yeah, so it's essentially what you're describing is a set of constraints on. Remember, I said that it's a policy with respect to like when the validator set doesn't exist. So what you're setting up is the framework whereby if you follow these policies, you're guaranteed always to be safe. That's the fastest way to say what the connection is. Your that's interesting.
Here, I'm going to stop share real quick. So, it's not quite a safety issue because somehow the safety means consensus safety. It's more like atomicity, which is in some way a safety notion, but it's not like consensus, right?
What I mean is you need atomicity in order to build the sort of end-to-end safety. So you're building up a series of
Yeah.
a series of properties that are necessary in order to guarantee that to have the safety proofs that you had before carry over into the sharded solution.
No, so my kind of like point of view is that like, oh, the safety proof carries in kind of for free. As long as we can actually do the like run the safety oracle, right? And the thing that you need to run the safety oracle and that the binary kind of layout provides is like the ability to tell, some kind of bounded thing that you need to look at to tell if a block is safe.
Mm-hmm.
And somehow, okay, the requirement for maintaining atomicity does potentially undermine the safety of blocks, right? Because, a block over here that needs to maintain atomicity with a block over there might end up being orphaned over here.
Mm-hmm.
But in this solution, the hierarchical solution, somehow that totally happens. And the way the solution is that the shards that are lower in the hierarchy basically depend entirely on the ones in the hierarchy for security.
Right. That's exactly what I said. You just said in different words what I said. So what I said was, in order for the safety proof to carry over, you have to have some constraints with respect to the hierarchy. Otherwise the safety proof doesn't go forward because you don't have the proper relationships amongst the merge blocks effectively. So
well, I think it's still the safety proof. I mean, it all still works. I mean, the setup works whether or not you can actually detect safety, right?
No, like if there's no relationship amongst the merge blocks and they just do willy-nilly whatever, the safety proof does not carry forward. You have to have a particular set of constraints on the information on the merge blocks in order for the safety proof. Because you could just have arbitrary nonsense.
Allow them to do willy-nilly. Somehow, what you're saying is that like the willy-nilly values are allowed to be values of consensus. Whereas, like, kind of what I'm assuming is that the values of the consensus
cut out, so
kind of only.
You're cutting in and out, and I can't get everything you're saying.
Sorry, somehow the way that maps onto my world is that like what you're saying is that the values of the consensus could be willy-nilly.
No,
whereas
I'm
like
just
I
saying that the way you merge them could be willy-nilly, so that you pick a few from this consensus over here and a few from that consensus over there, and they're not consistent, and so that's that you need some kind of consistency across the merge in order for and that's effectively what your definitions are guaranteeing, right? So like with respect, like Michael Birch and Kyle and I were all talking about whether or not a particular merge discipline exists at runtime or exists at compile time. That was sort of our one of the substances of our discussion. And what I was saying was, well, you can for sets of names, you can always construct certain sets. Like you can always construct the union of those sets, right? And what was sort of confusing in our discussion was, but there might not be a validator set that exists that is currently validating for all of those names. And then what you have to do is you have to make a decision as to whether or not what to do about that.
Well, the issue was slightly more subtle than that, I think, because
fair enough.
We were talking about how you could always guarantee the existence of a union because we were also thinking about a tree structure. But because the existence had to be somehow higher up in the tree, you might end up with processing things horribly inefficiently because you'd have to sort of force up code that should have been run locally. But I guess that's neither here nor there in terms of like how to line up
Yeah.
Vlad's thing.
Yeah. All I'm saying, Michael, is like I want to divorce the validator set discipline from the power lattice, the power object of names.
Yeah,
So,
totally. No, I definitely
right?
see what you're saying.
Yeah, and then
that makes sense.
Right, and then sort of the piece that Vlad is saying is that there's this minimal discipline on that validator set that will make the Casper safety proof go forward.
Wait a second. So I actually have said nothing about the validator set at all.
What you said is that they behave according to a particular merge discipline, which is effective saying something about the validator.
So so I think the assumption that's setting us apart here is that like I'm kind of assuming that all the blocks are valid for now, because for now I'm not even talking about validators and who's making sure that what's valid. And so I'm speaking at the level of abstraction where I'm only looking at the pre-block pointers and the kind of like the like hash links in the sharding thing.
Which is going to have an impact on which validators are handling which blocks is the discipline that we're talking about here.
Yeah, sure. And to me, that's like I mean, I didn't say anything about that. I think it's important and definitely part of the protocol.
I believe that you are. I believe that you are saying something about that.
Why?
That's implied by the constraints that you're giving here.
Well, I mean, it's not implied in the correct by construction framework. Well, it depends on which step, right? It's not in the like core part of the safety proof, but it is in like how we guarantee that nodes have a common future state.
Right, and that's going to then impact how you realize the merging. There's a discipline there that on the merging that's going to make your safety proof go forward. If you merge, there's some merges that will not be safe, and that's why you have constraints at all. Otherwise, you could just get rid of all of those constraints.
So I think maybe so if we take a look at the fork choice in enforced atomicity as opposed to the safe, like just the atomicity of safe blocks, there you kind of have the case that like any fork choice has the atomicity of merged blocks. So like it can't really be that the merge. There's no way that like if I'm on shard 111 and you're on shard 110 that we don't have like consistent merge blocks, because like all the blocks we've made with merging our parent were guaranteed atomicity by the fork choice rule. So like they definitely are included in this fork if they were included in the parent.
Because the binders. Yeah. So there's two different. Oh, I see. So Rao is asking a question, and then Michael is responding. Sorry, I thought you were responding to Vlad.
Oh no, sorry, I wasn't weighing in on your discussion. I was answering.
Yeah. Okay. Yeah. So yeah, now I agree. And okay. So again, I think we're just in violent agreement. We just use different language for how to talk about this. If you there are ways to merge which are simply going to be going to produce non-safe results, and then there are ways.
Right. So what I'm saying is like, oh look, like I can have my fork choice rule. Like so I'm saying like, oh look, I have a fork choice rule that guarantees that doesn't happen, but it doesn't know anything about like the data in the blocks.
Yeah, but we're not. In some sense, we're not really talking about the data in the blocks, or really at the level that we're talking about. The names are just used to carve up the sharding part. They're not really, they're not used for the data in the blocks.
Yeah, sure, but
the fact that they correspond is like a a happy accident.
Well, I mean, so
So-
somehow like there's like the pre-block pointers, which like the merge blocks have more of. You know, I mean, and then that's not. I don't consider that to be part of the data. I have like the pointers and then everything else in the data, basically.
Yeah, I understood. So we kind of get that for free because of the way we're structuring our blocks with respect to we carve up transactions using names, and so the names are going to give us all of the thing that you're talking about. It just falls out because we have this extra structure on names, and transactions are built on top of names. But we don't we don't know anything else, right? This is just a way of carving up the blocks in some sense.
Yeah. So that's what I'm wondering. So basically, like, I think that one of the main differences between our approaches right now is like, I am not thinking very much about the underlying VM. I'm just doing this like whole kind of blockchain trick where you're just like, okay, well, let's just get a replicated blockchain rather than the actual VM that will replicate that is the target. And I think that, like, you know, as a result, like, I don't know anything about the transaction type in my sharding spec, right? Which I think in some ways
I understand,
nice, and in some ways well, actually, so let me
sort
describe
of
this.
do because
it's somehow it's like easier to specify this way, and so it's just like going to be quicker to iterate, or like I'll have something out sooner in terms of just like a spec for people to study.
I don't know. Okay. I mean, I think I have a pretty detailed. Anyway, okay.
Yeah, that's what I'm saying. So the more details there are, that's the nice thing. So the nice thing about my current setup is like somehow, okay, it gives like a really, I don't necessarily think it's like the best protocol, but it's like a really, really simple thing that lets you see the kind of very basics of sharding.
Okay. I mean, you're going to have to talk about the internal structure of your merge blocks, because the merge blocks need to know information about the sharding, and that's exactly isomorphic to the information that we're talking about with respect to names. I mean, you laid it out. Names are sequences of binary strings, and you have that. You have that right. They're sequences of zeros and ones, so they're binary strings. So you have so you've already got the internal structure that we're talking about, and the reason you have that structure is because that's necessary in order to encode a particular kind of tree structure. And the reason the tree structure is there is because there's a representation theorem from what you need in order to talk about names at all and trees. And so all of this is necessitated, you know, by an extremely abstract characterization, which goes back to 1996.
Interesting. So I still have hopes that like we can break from the tree shape. You know, I'm not 100%, but
well, again, what? Yes. So I'm not saying that you have to have a tree shape. What I'm saying is that tree shape is adequate. In other words, there's a representation theorem. You can always do it in terms of trees. Do you have to use trees? No, but you always can if you want to. So
I mean, yeah, I here's how. So here's like how I agree with most of what you said. So I mean, let's see if I've understood. Kind of by even by firstly by giving the block structure, and then further by restricting which merge blocks are allowed. I'm kind of doing a lot of this namespace management.
Yep.
And actually, in my block structure itself, I have like basically block shard IDs in all the blocks.
Yep, exactly.
And it turns out to be like extremely useful. I am not sure. I mean, the spec, I was working on a spec without that, and it was much less pretty. So the shard IDs actually turned out to be quite helpful as something in the block.
Yeah, and that's ultimately what's corresponding to the name part of our transactions. All they're doing is providing exactly what you're doing with your shard IDs.
So I mean, I think somehow there has to be some indirection between the names of the transactions and the names of the shards.
It turns out that you don't need it, and it actually just ends up getting in the way.
But then you can just get DOSed, right? Like, what if everyone just like makes transactions to the same shard?
Because there's what we mean by indirection is different. I thought you were talking about, do you need an indirection? Do you need any more expressive power? You don't need any more expressive power. With respect to DOS, what you don't know is what constitutes any sort of semantic component of the transactions. All you know is that transactions have to do with I/O across these named locations, but you don't know to know the name spaces or correspond to the validator sets, and that's how you avoid being DOSed, because you don't know whether a particular namespace is always served by the same validator set. You don't know whether they're whether the validator sets are evolving. All of that is what all of that indirection, which is what I was trying to provide very carefully in my arguments with Mike, Michael, and Kyle, is necessary for avoiding exactly what you're talking about, DOS.
What about the relationship between like the fork choice rule and the shard structure? It sounds like somehow like the tree structure is fixed, right? Or
No, the tree structure absolutely has to evolve.
Okay, so can you tell?
All I'm saying is that at any given time, you're going to have a structure which is adequately represented by a tree.
Okay, but so I'm just trying to figure out if like how exactly the transactions relate to where in the tree your COM events are, or whatever exactly the reductions are happening.
But which tree? There are
the tree of shards.
Two like trees. There's the abstract tree of the namespace itself, which is fixed for all eternity, right? That's the power object of the set of all names. And then there's the concrete tree, which is the validators that are serving those transactions, the power set of the validator set, right? And then that power set is evolving over time. And then there's a relationship between that and the power object of the set of all names. And that's changing over time as well. And then it turns out that I just demonstrated that for every single contract that's been decorated with these kind of groups, these static declarations of groups which control the name flow, you can absolutely calculate what groups are necessary to deploy the contract. And then from there, you can make a decision as to how those groups are mapped onto validator sets. And that decision is what protects you from DOS. Does that make sense?
Yeah, but I'm still not seeing kind of how that interacts with the whole. Well, I'm not. Somehow I was imagining that the fork choice rule was like along the lines of one of these trees. And now I'm thinking that, maybe somehow you guarantee atomicity without having consensus on the shape of the tree.
I think the general idea of how to guarantee atomicity is to say that a given contract, like within a given contract, a I/O event, one of these state reductions that happens in exactly one place. So if you have a mapping from the namespace in which this IO event occurs to the validator set, that validator set, okay, in what order did this event occur? And did it occur at all, I suppose, as well?
Exactly. That's right. So
then other validators, I guess, but I guess what Vlad's question is if you have like related IO events, then how do you guarantee that order? And I think Greg's answer would be, if they're related, that they would have been in the same namespace to begin with, so the same validator set would have gotten them up front. So this sort of atomicity is guaranteed by the fact that the same validator set always gets them.
But how do you pass something from one validator set to another?
That's the evolution of the homomorphism, which, as far as yet.
Sorry, which as far as what?
As far as I know, that's not specified as of yet. Like how that homomorphism evolves over time isn't specified.
Right,
Okay.
which we're trying to leave as flexible as possible, so that we can explore different disciplines to see which one is most efficient. Right now we have the tree discipline that Kyle and Mike have been exploring. What I'm trying to do is to simply lay down exactly what the desiderata are on that discipline, so that we can have a wide range. I got a minute now.
Yeah, I've got to run also.
But this is great discussion. I think we're getting really close now to starting to make all the pieces fit together. So let's keep at this, because it's exactly the sharding discussion that drives a lot of the whole namespace architecture. Yeah. So
Yeah, totally.
I'm very excited about this. I think this is really good.
Sweet. Yeah, I'm excited. Excited to see what we'll dig up.
Cool. And we'll see you in Seattle.
Yeah, definitely. In
2
like
weeks,
a week and a half.
A week and a half. That's right. Awesome.
Cheers.
All right. Cheers, guys.
Bye, everyone.
Ciao.